Hey Santino, could you go get me a CT from the workroom?
Yeah, sure. Do you want a big one or a little one?
Well, we have to monitor the main breaker current in the switchboard, and it has to be highly accurate for metering and protection and go around 4 different 500 MCM cables, so...
So a big one. As long as it fits around the wires, it'll work, right?
Well, sometimes that's true, and there's actually a lot of different things to know about CTs because you have different ratings, different classes, different high-frequency ones for measuring different transients.
I didn't know that. Now, I know you've been working on some new demos with CTs. Hey, is there anything else you could tell me about current transformers?
Yeah. First, let's back up a little bit and define what a CT or current transformer is. A CT is a current measuring device that is used to safely reproduce a low-level current that accurately represents a higher current level for the purpose of metering and protection. Let's start with a simple explanation that describes the most common ways of calculating and measuring current using current transformers. By applying Maxwell's equations, specifically Ampere's law, we can say that if a magnetic field is integrated around a closed loop of wire, the value of that integral is equal to the net current enclosed by the loop. CTs are closed loop instruments consisting of a magnetic core and a secondary winding around the core. The primary winding of the CT, the main loop, has the wire with the current we wish to measure pass through the center of the core. The primary winding that carries the main current is said to have a single loop or winding. The wire produces the magnetic field that drives the current on the secondary winding, which is used as the output of the CT. The current on the secondary winding is proportional to the current flowing through the center of the core. Typically, the secondary rating is 5 amps or 1 amp. For example, with a 1000 to 5 rating or a turns ratio of 200 to 1, when 1000 amps flows on the primary circuit, 5 amps would flow on the secondary winding. Current transformers are primarily used for metering and protection applications and come in various sizes, shapes, and ratings. CTs can be solid core, split core, or clamp-on styles for both low voltage and medium voltage applications. Solid core CTs are generally more permanent and are most commonly found for metering and protection in switchboards, panel boards, and switchgear. Split core and clamp-on CTs are generally used in more temporary applications such as power quality instrumentation. For permanent applications of protection and metering, CTs can be found anywhere from generators to transformers to connected loads, or anywhere we want to monitor current flowing in the system. For example, utilities use CTs at their customers' incoming service to monitor the current and power usage for billing purposes. These CTs must be extremely accurate and are considered revenue grade since they are used for billing. Permanent CTs are also used to monitor power and power factor so that real and reactive power can be optimized. On the protection side, CTs can be used in combination with trip units for low voltage circuit breakers and relays for medium voltage breakers to trip the breaker when there are overloads or faults on the system. Many circuit breakers have built-in CTs used to monitor current. As a point of clarification, a lot of people call CTs sensors when they are mounted inside switchgear or circuit breakers, but the functionality and purpose is the same, to get current measurements to a useful level. A single CT is generally needed for each phase and neutral to monitor current, but for ground fault protection, a special type of CT is used. All of the phases and neutral conductors go through the ground fault CT, and if any residual current exists, in other words, current comes in on one of the phases but doesn't return on the other phases or neutral, then there is a ground fault. In your house, this is triggered by a 5 milliamp level, and industrial plants, this may be 30 milliamps or even a couple hundred amps. Ground fault protection is generally for personnel safety in homes and equipment protection in industrial applications. In medium voltage applications, a common misconception is that the insulation of the CT needs to be rated for the line voltage that the CT is measuring, for example, 13.8 kV. However, this is not the case because the CT is installed around an already insulated and typically shielded conductor. Most CTs and secondary winding insulation is rated at 600 volts. In medium voltage switchgear, the CTs are physically mounted around an insulating material or use physical separation to insulate the CT from the energized bus with an air gap. For all protection applications, CTs must be rated to accurately measure the high currents that are possible during fault conditions, usually 20 times full load amps, so that the breakers can trip in the proper sequence without saturating, which yields an incorrect result. CTs come in many different ratios, such as 100 to 5, 300 to 5, 5,000 to 5, 60 to 1, and some have multiple taps where the ratio can be selected in the field or for a specific application. Let's take, for example, 300 to 5 amps, meaning that a wire carrying 300 amps AC flowing through the core will produce 5 amps on the secondary winding. Most CTs have a 5 amp output, but others have 1 amp. So when interfacing with a meter or circuit breaker, the correct multiplier must be used that will convert the 5 amp or 1 amp to the actual measured value. But even though the current steps down 300 amps to 5 amps, the voltage will step up on the secondary winding. An open circuit on the CT secondary winding can have dangerously high voltage of thousands of volts. When CTs aren't in use, they should always have their secondary winding shorted for safety by using a shorting block or a temporary jumper. All CTs output a current that is then used for metering, but temporary CTs, like those used in Fluke and other power quality instruments, add a terminating resistor on the secondary winding so that they output a voltage and can be open circuited when connecting the meter. With this resistor, these CTs typically have a rating of 10 millivolts per amp or 100 millivolts per amp. The lower range ratio is usually used for secondary measurements, in other words, clamping onto the 5 amp secondary of another CT. Sometimes the current value is too small. A CT may not be accurate at less than 10% of its full load rating, so one way to increase the amount of current flowing through the core, especially for temporary metering, is to loop the primary wire several times through the core. For example, for a 500 to 5 amp CT or 100 to 1 ratio, looping the wire 5 times through the core will make the CT ratio 100 to 5 amps. So if 20 amps of current is flowing on the primary circuit, instead of 0.2 amps, 1 amp of current will flow on the secondary, making the measurement more accurate. CTs come in a variety of accuracy classes. For example, the ratio of primary to secondary current error of a Class 1 CT is 1% at rated current. A 0.5 rated CT is 0.5% or less. The accuracy of these devices is very important for protective relaying and metering. They have specific requirements for overload currents in excess of the normal rating to ensure accurate performance of the relays during system faults. A current transformer can have a range of ratings from C10 to C800, which is related to the secondary winding output voltage capabilities and VA rating of the CT. In simple terms, this means that a CT with a higher rating can sustain more burden on the secondary without saturating. For example, a C400 current transformer can have a burden that would drive a maximum of 400 volts. Based on these tables, a C400 would have an error of no larger than 10% at 20 times normal secondary current with a secondary burden of 4 ohms. Manufacturers will often offer a graph of the excitation performance of a particular CT. The graph allows you to determine the performance of the CT over the entire range of secondary current and ensure that the CT will function as required. This is an example of a typical CT saturation curve that shows the linear relationship and saturation point of a CT. Using a special tester like this one, current transformers can be tested to verify CT ratio and saturation curves. Generally speaking, CTs are fairly linear within 10 to 90% of their ratings, but may change significantly outside of that range. When operating outside the ratings of a CT, the magnitude of the secondary voltage above which the output current ceases to linearly follow the input current is called the knee point voltage. At this point, the CT has been saturated and its measurements can no longer be relied upon for metering. For protection CTs, this is especially important because these devices can see 20 to 30 times rated current during faults. In addition to CT saturation, the maximum frequency range that a CT can measure is typically 3 to 5 kilohertz. For most applications, this is okay since the harmonics on the power system are typically within this range. However, for high frequency applications like transients in the hundreds of kilohertz or megahertz range, special highly accurate CTs like these Pearson CTs can be used. CTs have polarity dots, arrows, or markings indicating current flow direction. The primary wire enters the CT on the side indicated by H1 or P1, and the load side is indicated by H2 or P2. When a CT has an arrow indicating direction, the arrow points towards the load. The current on the secondary comes out of X1 and returns on X2. A common problem when using CTs is after installation, a negative power is measured. This can happen if the primary orientation or the secondary wiring is backwards or a setting is incorrect in the meter. Additionally, CTs can also experience a phase shift between primary and secondary windings, which can range between a few tenths of a degree up to 6 degrees. That phase difference can make power measurements incorrect, even to the point that power may look like it is incorrectly flowing out of the load. Like all transformers, CTs have volt-ampere or capacity ratings. CTs have limits to the number of devices and length of wire that can be connected to its secondary side, which is called the burden. Items that contribute to burden are relays, meters, and wiring. The best way to reduce burden is to keep the conductors between the CT and the metering devices as short as possible, or increase the wire size to reduce resistance. The burden for today's modern electronic relaying and metering is very low compared to older equipment, but care must be taken to ensure CTs are not overloaded or inaccurate current measurements or protection will result. In addition to CTs, there are a few other ways of measuring current, including current shunts, Hall effect sensors, and Rogowski coils. One of the easiest ways of measuring current is with a current shunt or shunt resistor. By using Ohm's law, a known value sense resistor in combination with a differential voltmeter can be used to measure the current passing through the resistor. Because the resistor is small in value, the voltage drop across it is also small, but the value of current can actually be quite large. This method can be used to measure both AC and DC current. However, as the current that is being measured increases, implementing this method requires the use of large, high current rated, and low ohmic value resistors that requires making a break in the circuit and adds an additional electrical component to the system. Just as shunt resistors can measure both AC and DC current, Hall effect sensors can also measure AC or DC current. Hall effect sensors require an additional DC supply to produce a constant current flow in a semiconductor, creating a constant magnetic field. When another magnetic field interacts with the Hall effect field, it produces a change in current of the semiconductor and the sensor detects it. The strength of the detected field is proportional to the amount of current. Hall effect sensors are used extensively in UPS, solar, and microgrid applications for monitoring DC currents. A disadvantage of Hall effect sensors is that they require a DC voltage source in the form of a battery or fixed power supply. Drift can also be a potential problem, requiring them to be compensated periodically through a degaussing or calibration process. Many multimeters utilize a combination of CTs and Hall effect sensors in order to get an accurate current measurement. Finally, Rogowski coils are an open-loop current transformer using an open-air core with a very low inductance that is capable of measuring very fast transient currents and AC currents. Due to the low inductance, the signals a Rogowski coil generate are very small and require amplification and a DC power supply like a Hall effect sensor. Rogowski coils are used for current monitoring in precision welding systems, arc furnaces, and other electronic equipment where high-frequency measurements are required.
This thing is heavy. Ugh. Man, I didn't realize there's so many different ways to measure current.
Yep. And here at the Power Systems Experience Center, you can see all these ways and more. Contact us or your local Eaton representative to schedule a visit to the Power Systems Experience Center today.